Okay, let's start looking at the mathematics of the Laplace transform. We're going to start here in Mathcad Prime, and then we'll move over to MATLAB, as we've done before. So we'll start here. Let me blow this up a little bit in case you're looking at this on a small screen. Okay, there's my complex exponential. That's the kernel function for the Laplace transform. Well, I think we all know this, but let's just expand this out. And I'm going to type in expand in Mathcad, and it turns into the product of a decaying exponential and a complex exponential. Well, that's a decaying exponential, so that basically defines the envelope, and that right there is the sine, cosine plus I sine term. So that's what we saw on the board. Now, in order to plot it, I need a frequency and a sigma term, a damping term. So for convenience, I just said omega equals pi, and I need a damping term. I just arbitrarily selected 0.01 because that made it clear that the amplitude of that sinusoidal wave is decreasing. So let's go down here and see what this might look like. Put in t there. Let's put in f of t there. What's going to happen? Well, nothing. I get an x right there, and there's nothing else going on. Well, what's up with this? Well, that's a complex term there, and I haven't acknowledged that over here. Now, if I decide to plot the absolute value of that, I'm going to get basically 1 everywhere. This is just kind of noise. This is computational. It's round off error. And see all those 1s over there? That's because the amplitude of this really is 1. In complex terms, that's a unit circle. So I obviously don't want the magnitude. How about let's plot the real part of this, because that's what the Euler relation said to do. I want the real part. That's going to be a cosine term. Ah, there it is. Okay, there's my cosine right there. That's exactly what I want. So let's do this. Let's add one more trace, and let's use the real part of now this L of t using that different kernel function. I don't like that color much. It's hard to see. Let's fix that. Let's make it bright red. There we go. And let's maybe make this there. Now you can see it. In the background, there's this dark blue sinusoidal term. That's the Fourier kernel function. In the foreground, you can see this bright red decaying exponential. That's what the Laplace kernel looks like. And so the Laplace transform is a natural tool for trying to describe oscillating systems where there's some damping, which, practically speaking, is almost all oscillating systems. All right, with that done, let's go over to MATLAB and see what tools we have available there. Okay, I've switched over to MATLAB now, so we can explore Laplace transforms here. Now, unlike the Fourier transform, if you're working with Laplace transforms in MATLAB, you're probably working exclusively with the symbolics toolbox, the symbolic processor. So to do that, let's define some symbolic variables. There we go, a, t, and y. All right, a is just some constant, t will be time, and y will be the result, perhaps. Let's define a function that's an exponential. So we've got this as a symbolic function now. You can see it over there. Well, what would happen if we took the Laplace transform of that? There it is. It's 1 over a plus s. And that's s being the Laplace variable. That's sigma plus I omega. Now, one of the really cool things you can do in MATLAB is you can define f of t as a symbolic function or symbolic variable without specifying what it is. Watch this. This is really cool. Let's type in sims f of t and s. Now, I'm going through the MATLAB Help Center. That's where I'm finding this. So if you want to go online, go to mathworks.com/help/symbolics, and you can, symbolic, I guess I should say, and you'll find all this. Or just go to Google and type in help MATLAB and then Laplace, and you'll get there. So I'm going to type in df equals Right, type that in, and it took it. Watch what happens. There. What this means is, if you want to take the Laplace transform of a derivative, what you get is the Laplace transform of the time domain function, whatever that is, times s minus f of 0. And this is big. We're going to refer to this later when we start solving differential equations. There's two interesting things here. The first is that s. What that shows you is that when you're in Laplace domain, differentiation becomes multiplication. So differentiation in the time domain is just multiplying by s in the Laplace domain. And what this part right here means convert or transform f of t into f of s. And the other interesting part is this right here. That's f of 0. That's what's called an initial value. One of the forms of differential equations you're going to see an awful lot is one called an initial value function. And the initial value is built right into the Laplace transform. So you can see that it's just going to be really useful for solving differential equations when you get that far. Now, the Laplace transform in MATLAB works on array inputs, and there is an inverse Laplace transform, just like there's an inverse Fourier transform. So the importance of the inverse transform is that to solve a differential equation, remember differential equation is just an equation with a slope in it. It's nothing more than that. But they're hard to solve, so we take the differential equation in, say, time domain, transform it into Laplace domain, where it becomes, working with it becomes simpler, do some manipulations in Laplace domain to find the answer in S space or S domain, and then inverse transform it back into the time domain. Well, that's what the inverse Laplace function does, and it's just called I Laplace. To show you how the inverse Laplace works, let's just clear all this stuff. Type sims f of t and s, and we'll say f of t equals 1 over t. It's a time domain function. There it is. And we'll say f of s equals 1 over t, t, and s. Let's see what we get here. Okay, that's correct without being very informative. Let's do this. Whoops, spell it right. And hit return, and there it is. There's 1 over t again, just like we had before. So there's how the inverse Laplace works. Now, as we get into differential equations and Laplace transforms for solving differential equations, this will make more sense. This is just sort of kind of a teaser. This is just something to get you interested in what's coming next. So we've seen what the kernel function looks like in Mathcad, and then done Laplace transforms and inverse transforms in MATLAB. I hope this helps, and we'll talk to you next time.